I hope that many of you have had the chance to actually appreciate a sky like this in a dark night in the summer. If you haven't, then you should definitely take the opportunity to do it whenever it's possible. And what we're seeing here is really our galaxy. Most stars here are relatively close by, but you can see them defining the disk of the Milky Way, and all these darker patches are actually caused by dust, not because there's less stars. Nowadays, we do know that the Milky Way is an SBC galaxy. We'll see exactly what that means. And it actually measures about 30 kiloparsec in diameter. So if you're measuring the disk or if you're measuring the halo, that's about 30 kiloparsec. We also know, even though there's some big uncertainties actually, that the Milky Way has about 100 billion stars, and that the mass in stars is about 5 times 10 to the 11 solar masses. Currently, star formation essentially happens in the disk. The Milky Way is forming something like 3 solar masses per year. You may think that this is a lot, but it's actually very little, especially for the amount of mass that the Milky Way already has. And in many aspects, I guess the Milky Way could be considered a dead galaxy, although it is still a spiral galaxy forming stars. The Milky Way is also made of these essentially 3 main components. We have the bulge that sits in the center. We'll see that in the center of it, there is actually a supermassive black hole. There is a disk that is essentially very thin, and we are essentially here midway from the bulge to the edge of the disk. And then there's a component which is spherical, the halo, where globular clusters, which were crucial to determine our position within the galaxy, exist. Unfortunately, it is not possible to just get on a rocket, get out of the Milky Way, and then take a selfie with it, showing something like this. But using the data and observations that we've gathered over the years, we actually have a decent picture of how the Milky Way sort of looks like and our position. In this case, what I'm using is a real picture of Andromeda. The Milky Way is a bit different from Andromeda, but not that dissimilar. What we can see is that if this was the Milky Way, it would actually measure 30 kiloparsecs side to side. That's about 100,000 light years. And we would be around here, 8 kiloparsec, or about 26,000 light years from the galactic center. And it's also important to realize that we're looking at the product of a lot of physical processes that took place during 13.7 billion years. And in further sections, we're actually going to be looking in detail of what that physics is and what kind of processes led to galaxies like Andromeda and our own Milky Way. Once we started studying our own galaxy, the Milky Way, we realized that there are different stellar populations within it. Remember that in section 8, we introduced the Arvid classification scheme that allows us to classify stars in terms of their temperature. However, for a fixed spectral class, stars can be more metal poor or more metal rich. That is just a very different classification scheme. Historically, the first stars we found were stars like the Sun. They're very metal rich, and because they were the first stars to be discovered, we named them Population 1 or POP1. Now, stars like the Sun that are metal rich are the ones that are still being born in, for example, the spiral arms. Because of this, in our galaxy, essentially all O and B stars that are very massive, they're all population 1 stars. However, specifically if we look at the galactic bulge, and even more so if we look at some globular clusters, we can actually find stars that are much older and that have way less heavy elements. Those stars, because they were kind of the second class to be discovered, we call them population 2, and typically they're very red. And the reason for this is because all the blue population 2 stars are long gone. It is, of course, very important to understand that the classification between population 1 or POP1, population 2 or POP2 are very different from the spectral classes. Within population 2, we still have spectral classes running from O to M, but the big difference is for population 2 stars, if we're observing them in our own galaxy, essentially all the hot spectral types are gone. So typically population 2 stars are said to be red because only the red and colder one have survived after something like 13 billion years. Now, by studying the galaxy in detail, we realize that the disk is mostly dominated by population 1 stars like the Sun. It means they likely form much later on. But if we look at the galactic bulge, we actually see a mix of population 1 stars, which are metal enriched, and those that are quite metal poor as well. While in the galactic halo, especially for globular clusters. They're essentially just made of population 2 stars. Now, as part of this classification scheme, it is important to note as well that the other class is called population 3 or POP3, and by definition, POP3 is even more metal poor than population 2. And by definition, population 3 stars are made of just hydrogen and helium, essentially. Therefore, it is important to point out that this scheme can be very confusing. Population 3 stars were actually first-generation stars, population 2 were second-generation stars, and population 1 stars are at least third generation, but many might be fourth or even fifth generation. Within our galaxy, we can use, for example, the Doppler effect to measure the orbits of stars. And what we've realized is that essentially stars within the disk, they all orbit in the same direction. And this also means that the disk is quite thin, but there is some wobble essentially caused by the gravitational pull from the disk that gives the disk some thickness. It is thin, but not infinitely thin. However, when we look at the bulge, we actually realize that stars are rotating in random directions. This is what makes the bulge more like a spheroid and not a disk. And also, the same thing goes for the halo. Star clusters in the halo, globular clusters, are essentially rotating in random directions, and therefore, if you combine all those orbits, you're actually recovering more of a spherical structure and also not a disk. Historically, studying the galactic center has been really hard, especially because there's a lot of dust in the line of sight. If you look at this real image, you can actually see that this is the real galactic center, and it's quite odd because you expect things to be rotating around where there's the most mass. And therefore, you expect the galactic center to have a lot of stars. But when you look in the optical, it's actually quite dark. It almost looks like there's not a lot of stars. Of course, that is not true. The reason why this looks dark is because of dust and not because there's not a lot of stars. And therefore, once we had access to long wavelengths, infrared, mid-infrared, and even in the radio, this is where the game completely changed. By observing in the radio, we can actually see all the way down to the galactic core. And we can see this incredibly bright source that is called Sagittarius A. We now know that it's actually powered by a supermassive black hole. But on top of Sagittarius A, we can actually see lots of supernova remnants. This means that very close to the galactic center, stars are still sort of forming, and we're seeing the remnants of some of the O and massive B stars as they went supernova. These observations in the radio were really crucial to start establishing this puzzling source, Sagittarius A, the brightest radio source within the entire galaxy, as a potentially very compact object that was very mysterious. And it was essentially through many, many attempts, including those that use adaptive optics and in the near-infrared, by measuring orbits of stars that go really close, that recently it was possible to actually measure the mass of this black hole, leading to the Nobel Prize in 2020. An important question we could ask, especially because this led to the Nobel Prize in Physics in 2020, is how is this done? And in the video, you can actually see the data that was used to make the discovery. In very simple terms, by measuring all the orbits of all these stars and essentially making very simple assumptions, we can actually invert it. And because we can measure the average velocities of these stars that go really close to the black hole, we can actually measure a mass, infer a mass. And this mass comes out as 4 times 10 to the 6. 4 million solar masses contained in a very small amount of space. And this was really what provided the strongest evidence for the presence of a supermassive black hole that then led to the Nobel Prize. This was, of course, only possible by really taking advantage of the technique that we covered in section 6 called adaptive optics, and also using the infrared.